There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromide, lithium, beryllium, and barium. Isn't that interesting?
3, 2,
I hope you're all paying attention. There's going to be a
fire.
short quiz later on.
Okay.
There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury and molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radenzine, and zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Hi, everybody. I'm Chemical Charlie.
And I'm Pie Guy Pepin.
And we're going to do a little demonstration of a battery today. And we have a piece of copper metal, uncharged, Cu. And we have zinc over here, Zn, uncharged. In this solution, we have copper ions, Cu plus 2. Copper metal, uncharged, Cu plus 2. Here we have zinc. And in here, there's some Zn2 plus. Now, the copper ions have a greater tendency to get reduced, so they will gain electrons. The zinc has a greater tendency to get oxidized, that will lose electrons. So, and this is a salt bridge that allows the two compartments to maintain their charge. So
we are going to use that to power a tiny clock.
Okay, see this clock? It's not working. So let's hook it up to the battery, the electrochemical cell, and I'll show you that it does work. This is more of an academic cell than one that's used.
This isn't used for like.
Okay, now you can see that the battery
You can see
works.
it works.
Okay.
Well, this isn't the correct time.
Now, if I take the salt bridge out, you can see it stops working.
Because it needs to
Maintain electrical neutrality. All right, now it's working again. The zinc metal loses 2 electrons, becomes zinc ions. The electrons go through the battery, through the clock, and over here, and those 2 electrons are gained or added to copper ions, which plate onto the copper metal. And in the salt bridge, since you're getting rid of positive ions, 2 sodium ions, this is a sodium chloride bridge, sodium ions replace the copper ions that are reduced. And on the other side, you are creating zinc ions, so you need 2 negative ions to counteract the positive charge, so 2 chlorides do that. So you get a flow of electrons around here like this. And of course in here, instead of the electrons, it's ions that are moving. But it's moving in such a direction that you have negative going that way and positive going that way. Loss of electrons, oxidation.
gain of electrons, reduction.